me. Rob, thanks for having me. Core, thanks for putting this together and all the effort that goes into that. My name is James, and I am the lead R&D engineer at Zaner Company. It's a company in Kansas City, and we specialize in sheet metal work. And our niche is complex architectural parts, as well as some artwork as well. We're in Kansas City in the Midwest, and this is maybe what you guys are thinking, right? Like, oh, Kansas City, Midwest. It's a little dreary, right? But we got space, we've got tools, and we've got a lot of really interesting problems to tackle. And we've done a lot of projects, primarily in the United States, but scattered all over the globe. And while you might not know us, you may have seen one or two of our projects, or probably worked on one or two of our projects with this crowd. And each of these projects, this one being the Experience Music project, a foundational one for Zaner, where really they leveled up a lot of both the computation and the skills and strategies that we currently use today. But there's two things that are common between all those images and this one. The first one is they're all different, right? They're all vastly different shapes, different materials, different forms. But there's the second thing, which is they are all aspiring to meet the design intent, right? We're not a fabricator that says, no, we must rationalize your parts. It is, okay, you want to do this, we'll figure out how to do it. And this project really epitomizes that mentality. And so my talk is indeed entitled, Design Intent Does Not Equal Machine Instructions. And this is a crucial thing that we're going to explore through an active project that we're doing right now. And really the core of it is that we are developing so many sophisticated ways to develop geometry, parts and pieces, and more is possible by a single individual in AEC. But it all comes running to a dead stop right when you get to the point of manufacturing. And so what we're seeing here is this wonderful UI and interface for one of our CNC punching machines. So this is a turret punch, one of the coolest machines that exists in my opinion. And there's a few things to take note here, right? The UI is not great, right? That's just an obvious thing. But this is something someone's going to look at for 8 hours a day, right? They're going to see this thing, they're going to go through file after file after file. And the other thing is you'll notice that there's a worn away patch right here. You see that? Oh, you can't see my mouse. There's a worn away patch right where your hand would be. And can you imagine how many clicks it would take to wear away the paint on here? So this is a serious problem. And it's a problem because someone is doing this, and it's not a great place, and humans can be used in a much better way. The other problem is architects are paying for this, right? So if you're trying to do a project with a lot of different parts and pieces, you're oftentimes kind of developing a workflow that's going to lead to somebody wasting a lot of time clicking needlessly. And part of the reason that happens is that we've got a separation between all these different groups, and we have a vastly different level of sophistication between the tools that they're using. So if we go left to right, looking at designer first, engineer, and these roles sometimes mash together and kind of motion in different ways. But as you go from maybe a 3D CAD model, you've got a lot of control, to a CAD model that's sliced up and thicknesses are added and material information, attributes are added. And then it sort of goes downhill, right? We maybe drop it to a DXF, where now we have a 2D format, where none of these things can be parametrically edited. And then you eventually get to the machine operator who has a text file that they're going to run. And the most automated thing that they have at that point is like find and replace, which is a really common thing they do, right? It's like if the Z height needs to be adjusted, they're going to search in this file, and they're going to find all these things, and they're going to adjust it all at once. Because otherwise they have to go all the way back upstream to try and get that information. So there's an inequity in the way that the tools are distributed, and there's a really hard line that is causing a lot of problems. The other problem is that we have issues with the production machines we work with. So this is typically what a production machine, if you buy one, and this is an imaginary machine, but any machine that's going to do a large volume is typically going to have a workflow similar to this, where we're looking at doing the CAD CAM process maybe once to produce thousands of parts. And so in that way, that first tool pathing of things doesn't have to be sophisticated, right? You spend 20 or 30 minutes, tool pathing a single part, but you make 1,000 of them, that's okay, right? Because you're only going to do it once. At Zaner, we use these production machines, but we only have 10,000 files we're only going to run once. And so it blows up this initial step. And this is that bottleneck that I was speaking about, where your design intent, it's really easy to generate all these machine instructions, right, and all these unique files. But it's really hard to get through some of these layers lower down the line. So, and what does that look like? So when you're doing these tool pathing, why does it take 10 minutes? Well, oftentimes you're jumping between maybe 6 different softwares, and you're importing and exporting and converting, and each of these different machines is also in a different time period, right? And sometimes they have even outsourced their software and UI. So there's a lot of these issues, and I'm going to talk a little bit about a project that will remain unnamed, redacted for here, but it's working with a group, HKS and HKS Line, and it is, we'll just call it the Large Panel Project. And so the way this project looks like is there is 37,000 unique panels. And you might say, well, that's silly, why don't you just rationalize them? But once again, Zaner is not the kind of group that's going to say, architect, change your design and rationalize it. So we decided to meet this challenge. In this blue section here, we're seeing there's over 1 million hits, right? And then you sort of zoom out a little bit further and you start to see all these different parts and pieces. Each piece is made up of about, what is it? 1/8-inch thick aluminum, it's white anodized, and each one has these unique perforation pattern as well as a unique boundary edge, right? Because it's a doubly curved surface, we're getting all these different unique triangles. Scaling that up, and this is an important photo. This is where we were doing a lot of the initial testing, right? And so part of the way that this process worked out well is that we were involved really early on in the process during Design Assist, where we could really work with the architect to try and get through some of those barriers, right? And start to figure out what was going to be the most efficient way to get through this and actually accomplish these 37,000 unique parts. And so this little tiny triangle is actually embedded inside of it is all the information we need to produce all the punching files as well as the edge conditions and whatnot. The full-size panel looks like this. And the first step is, right, okay, if we're going to make these panels, how does the architect give me the information, right? You can imagine getting 37,000 drawings is not a super tenable thing. So instead, we worked with HKS and Heath May's group to design a text-based format that is basically encoding that information about the panel. So we have things like the global coordinate system as well as the local coordinate system and all the perforation data, you can sort of see zooming through there for every single panel. And he could transfer the 37,000 files to me in a small zip file. That was a really convenient way for us to handle that data, and so that we could focus on things more related to manufacturing. So now we started doing some regression and some studies on how we might nest these parts, right? And so we started to figure out what is the angle, the appropriate angle for this sheet to figure out the minimum waste on this. And we didn't have to worry about these files. So we're using the really sophisticated tools that we have in Rhino and Grasshopper and others that we can use to do these really great studies. And we don't want 100. We're using these really great studies in order to optimize our material utilization early on. We're dealing with fabrication data when we have these powerful tools, not further down the line once we're at a point where we don't have those, right? And so you might say, well, why would you use that machine? The trouble is we need the production volumes, right? Because we're doing lots of parts. And so we're kind of stuck using this software. And oftentimes we'll go around the software, right? For laser cutters and water jets, we'll write directly to the machine. It's controlling a position and it's turning a beam of water or laser on. But the punching machine is different. Oh, we don't have audio. So the punching machine is a little bit different, right? So this is the most complex machine I've ever programmed. There's lots of different moving parts. There's 30 different tools. It's hitting at 1,600 hits a minute. It can form, it can punch, it can score, it can do all these really wonderful things. It can also, you might notice that a really fancy thing just happened. The clamps actually retracted as it came over the top of it. And so if you imagine me skipping ahead and just programming right to the machine, it's likely that I'm going to mess this up and I'm going to crash this clamp. And we've done that. We've smashed the clamps and it hits with 25 tons of force, so it's kind of a big deal to do that. As well as there's lots of other tricky little things about you need to make sure you hit enough material, otherwise you'll sideload the tool. And so there's lots of these things that are embedded in the software that the machine manufacturer is designed for us. So going around it really isn't a great option. So we're stuck here. We've got a ton of these files and we have to get them through this machine. And so what I ended up doing was interacting with the machine manufacturer's software team to get access to their API. And the strategy was, if I can embed all the information needed for the punching into the files early on using things like Rhino and Grasshopper, when we have all this flexibility, it's really easy to go ahead and add these little tick marks for where the material is going to be held, add the indexing information for how we're going to track and manage the parts later on. And then I can deploy that on a massive scale. So we're looking at here, I'm producing 5,000 of these parts all stacked on top of each other with some help from some friends around here, a human and elephant, which elephant man is what I typically call it, that sort of combination. And then what the workflow ends up looking like once I generate all those parts and pieces, Now is where the fun happens. Where before we were looking at maybe 10 minutes apart, and at 37,000, you can do simple math. It's, it was actually past the date when we were supposed to be fully installed. And so it was something we signed up for. We're like, okay, we need a better solution. And so this is me now interacting with the machine manufacturer software in a way that we are sort of used to working, right? Is automating these things, ignoring a lot of the prompts and entering the end through things. And so now I'm actually processing all the tooling information at about 7 seconds apiece. And so I was able to do all the files and write on Grasshopper and all the processing in a matter of a couple weeks. And so, and what that looks like, and what's exciting about this, is we didn't rationalize. Look how beautiful, how it tweens between them, right? It's like the finest, sweetest little lines. And it's almost sad to think about that we would have rationalized it. And the promise of digital fabrication is that we should be able to do unique parts. We shouldn't have to rationalize it because the tool doesn't care if it's a little bit left or a little bit right. It's moving motors, right? So this is just zooming through. I think this is 2,000 panels, but you can kind of see the little green dot, right? So these are the parts that we were making, and we couldn't program quite this fast, but we can definitely generate them this fast. So don't mind the jitter at the end. That's you can ask James Wharton about that. So now we've made all these files. And I don't mean that. There's a little dummy panel in there because the triangles got too big, and so I had to throw a dummy panel in there. Okay, so then the end part here is that there's no way to get around this, right? We have to make these parts. It's a physical thing, and Zaner is right at that edge, right where we take all this really complex information and it turns into material. So we're punching these things, we're breaking these things. It's a manual process because we're making a physical good. And so there's no way around this, and that's why we need that production machine, because we have a high volume of parts and we need it fast. But now the bottleneck's not in the software. The bottleneck where it should be in the material. And so we go through, we make these parts, and we can also do some clever things about how we tie our models and things to our logistics. And so you're going to see Olivia here do the QC, and she does a very fancy thing here where she peels this corner back, and there's a little tool where you can, that tool actually hits 3,000 hits a minute. And it does this little tiny dot pattern that we can scan. So she scans that part in, and it gets loaded into our database remotely. So we can actually watch when it gets punched, when it gets broken, when it gets QC'd, when it gets patinaed, or when it gets anodized in this case, and when it shows up on site. And so we got this insane spreadsheet now that is, we can track the process. But that's impossible if you're just receiving a DXF. You're not going to sit there and type in each of those little dot codes. But it's really easy when we're in Grasshopper, right? When it's early on, and we're mixing these roles. So a little shout of how this works. You can see some of the features that were added in, little tabs and things that normally would be entered in at the point of programming. This is added in way earlier. Parts made, parts installed on the larger space frame, and I missed much on. And ta-da, right? It's perfect, right? Everything's great. It's not quite the case. It's there's these edge conditions, right? And I talk about this because I feel like honesty within manufacturing is important because we can't just gloss over like it's all super easy. So 95% of the panels are easy. The edges were a mess. So it broke all the auto processing features that we had in the software. And so what we ended up doing here is we needed to give it an origin point. We needed to give it all the same information about how the tabs are held on. But it only allowed us, and we wanted to do it as a nest. But the software was making us load it in one by one. And so you end up doing these jumping through all these hoops to try and trick the software into doing what you want it to do. And what this goofy line is doing here is actually you making a single boundary. So it's attaching my two triangles together, and it's putting dots in there so it won't punch because there's not a big enough space for the tool. And so another thing that you can do is trick the machine really well if you can apply your rules to it. And so this is where it gets a little bit goofy, right? Because now we can see these rules in action, right, for the last 5%. And you can see it sort of jumping to the edges where the mesh is trimmed. So if you are using sophisticated tools early on, then you can make it through these workflows. And in some cases, if we're lucky enough to have a machine manufacturer and a programmer, the one I was working with, his name is Herman Schwartz, who's willing and able and open to interacting with you, then you can get through these things and you can do the unique parts and you can do it affordably. So here are the parts getting installed inside. Loaded together, and each of these boxes is full, so I'm going to have to zoom through. But the key here is these roles are merged, right? So the person designing the parts was not absent from the person who was programming the parts. We had this conversation all together, and there were some really important roles that all worked together, and all the information was sort of embedded in this single process. So we had to break down the silos in order for this to work well. And production workflows just, they don't work well for architecture, because we're doing unique parts every time. Zaner has up to 50 to 80 active projects, and we have 20 engineers. And so automation has to play a huge role. We have to deal with lots of parts and pieces, and we have to do it quickly and efficiently. So is this a one-off solution? No. Cornell University, the local one here, we did another automation process that is closer to I think what is within reach for anybody working within academia and any place where you have an industrial robot, where multi-purpose tools are less strict, right? The Punch is an extremely strict machine, has lots of wonderful features, but also things that make it difficult to interact with. The robot is a generalist machine in ways. It's multi-purpose, and so it is open for you to create new and different ways to interact with it. So on Cornell, from a similar workflow, we could create the fabrication files, the robot instructions, and the shop directives all at once, and sort of cruise through there and combine all those roles together as well. In Acadia, I did a little demo of this where it was I try and live up to the claim that it is easy and do a little demo, but in this case, we're going to have to zoom through it. So the end of the line there was that this thing was a little finger, and we mapped some of the depth from an image provided by Morphosis to the rotation of these tabs, so we could rotate 500,000 unique tabs, which is different because I worked at a Ford Motor Company for a while, and the robots there were doing the same thing every day, right? Like you want them to do the same thing. If they're not, then there's a problem. But here we were running 4,000 panels on this, so 4,000 unique robot files, all produced via Rhino Grasshopper in the end product there. And you can sort of see how that works. And so it isn't a one-off solution that you can combine these roles, and robotics is a good way to do that. And we use robots in a lot of different ways, from shaping material to positioning and holding. For Hudson Yards here, we did a extrusion of silicone in sort of a unique way. And so I guess the moral here is that the production strategies for architectural projects it requires a fundamentally different strategy and a fundamentally different manufacturing technique, right? And so we always talk about how aerospace and automotive are so far ahead, and we should learn from them. In some ways we can't learn from them because they're doing something different than us, right? And so at Zaner we're working on pushing that exclamation point one space over, right? So design intent can, equal machine instructions. So we're trying to ruin it from and what you're seeing in the background there is we have ambition to have these sort of multi-purpose tools that we respond to the design intent and the design that architects bring us. And so instead of fitting the designs into our tools, we fit our tools around the designs. And so that's our key objective. And in 2 seconds, I was talking to Brian last night, and we were saying, okay, well, how is this content achievable by everybody? Like, well, we don't have $1 million machine. How are we possibly going to work on this problem? Well, a lot of my thesis work was on multi-purpose machines that were really inexpensive. And so working with Professor Nadia Peak, a collaborator of mine, and Alon Moyer, who is the CEO of this really excellent company that makes the tool called Shaper. It's worth investigating. We developed a kit of parts, a modular networking, a modular set of components for mechanical actuation, and then a network control system where you can plug as many motors together and make arbitrarily large machines and have them communicate synchronously. And so we also developed a cardboard version of this, right, where for $20-some you could develop a CNC machine, part these pieces together, and tackle all sorts of really interesting things and really see the systems integration problem through. And that way you can see all the different parts and why it's challenging, and so your workflows can become more machine-friendly in a way. That's it. Thank you.